Welcome everyone to our Ansys APDL series. In this video, I'm going to focus on 2D truss, in which we will see how we can use command prompt in Ansys for designing 2D truss and analyzing 2D truss. So let's focus on the example. What we have in here is basically a truss, 2D truss with the modulus of velocity of 1e8, the Poisson ratio of 0.3. And we are going to consider no displacement on the lower right corner of the truss, no displacement on the lower left corner of the truss in the vertical direction, and we are assuming there would be no out of plane displacement. At the same time, we are going to apply 1000 Newton downward load on the lower center joint, as you can see in here, and the dimension that we're considering is going to be 20 width, 20 meters, and 10 meter high. So let's look at the geometry that we are going to consider. The truss is going to have 5 nodes, and these nodes are defined as N1 to N5, as you can see in here, and we would have 7 elements that are going to connect the nodes in order to make the 2D truss of interest. In the second part of this video, I will show you how you can use command prompt in order to basically design a 2D truss and analyze it with Ansys. Okay, as I stated, in this video I'm going to fully focus on command prompt, and I'm not going to use basically graphical user interface. So let's start. The first step is entering the preprocessor. For entering the preprocessor, I have to write prep7. Now we are in preprocessor step where we can basically define the elements, the parameters, and also do the modeling, putting the material properties. So the first step, we want to use links because we are dealing with 2D truss. In order to define the links, I am going to write ET1 LINK 180, which is basically specifying the type of link that I'm using here. So hit OK. And then the next step after here is basically defining the section number for the link that I'm using. So in order to define the section name in here, I have to write SECTYPE 1 and then link, and then I can say enter. Now we have defined the section type. The next step is basically providing the cross section and the area for that cross section, right? So in order to provide that, I have to write SECDATA and then 1, which is going to be the cross section that we are considering here, and hit OK. Right? So now we have defined the cross section, we have defined the type of links that we want to use. At this stage, I'm going to provide the nodes and the geometry of the truss, and then we can see the geometry and basically the shape of the truss that we want to investigate. So for the first one, in order to put the nodes, the first thing that we have to write is n. So I'm putting n, then 1, then 0, 0. So 0, 0 is basically giving us the location, or let's say the coordinate of this node, which is located at 0, 0. The first one representing x and the second one representing y, and then hit OK. So the first node is defined. Now it's time to define the second node, which is going to be N2, 10, 0. The third one, N3, 20, 0. N4, 5, 10. N5, 15, 10. Now we have defined all nodes. The next step is basically defining the elements. Elements can be used for linking the nodes based on the given table that we already saw in the first part of this video, right? So the first element that we have is basically connecting node 1 and 2. Therefore, we would have E1, 2. So that is the first one, which is going to create an element between node 1 and 2. The second one is going to be E2, 3. Then E1, 4. Then we would have E4, 2. The next one is going to be E2, 5. Now we have defined the elements between basically 2 and 5. Then we would have E5, 3. And then the next one is going to be E4, 5. Right? So now we have defined all elements. So the question is, what are the material properties and how we can define material properties? Again, easily with the use of command prompt, we can write MP, EX, and the modulus of elasticity that we have considered. So I'm going to put 1E8 here, okay? And then hit OK. MP, sorry, I forgot to put 1 here. We just have material 1. So it is going to be MPEX1, 1E8. Hit OK. Then the next one is going to be basically defining the Poisson ratio that we have, right? MP, and then we would have PRXY for material 1, and that is going to be 0.3. Hit OK. Now we have defined the materials. We have everything ready, and the next step is basically focusing on the solution. In the solution step, basically we can apply the boundary conditions, and at the same time we can apply the loads that we already considered for the system. So in order to enter this step, we have to write SOLU. Now we basically in the step of solution, right? So at this step we can define the boundary conditions. So as you might remember, one boundary condition was related to node 1, in which we want to have a constraint for node 1 in both x and y direction. Therefore, we can say D, the displacement of node 1, ux, and then it's going to be 0. So that is going to be for uy as well. So now we have defined the boundary condition for the first one, and if you look at the node 1, you will see how it changes the shape of this system. You see we have the boundary conditions defined here, right? After this step, we have to define the boundary condition for node number 3. For node number 3, we are going to have basically the constraint in y direction. Therefore, it's going to be D3 uy, and then I'm going to put 0. So you see we have the boundary condition here, and we don't need any sort of out of plane motion, right? So we need to basically apply the constraint in z direction as well for all the nodes. So that is going to be D all uz and then 0. So we have applied basically the constraint on every single nodes that we have, right? So now we have the boundary conditions. The next step is applying the force. So the force is going to be applied at this node number 2 basically. So we will have F2, and then the amount of force is going to be basically in y direction, therefore Fy. And the value that I'm going to put here, based on what we saw in the slide, it was -1000, but I have decided to change it to -5000 and then hit OK. Now we have defined the force as well. As you can see here, the next step after that is selecting every component that we have and solving. So for selecting every single component that we have in here, we can write all cell. So we have selected everything, then all cell, and once it is done, we can write solve. So now the solution is done. We can basically jump to the general post-processing. And before that, I'm going to write here finish. Okay, so in order to jump to post-processing again, we have to write a line of code to enter to that general process. And let's say general post-processing. So we can write post 1 and hit OK. Now we have general post process. The next step after that is looking at basically nodal displacement, right? How we can do that? We can again write a single line of code here, PLN SOL, and then we can say, okay, displacement, the sum of displacement, and 0, 1. So that is going to give us the displacement and basically the nodal displacement and the plot for that one. Hit OK. You see that here we have the maximum displacement, right? And also the maximum stress being applied here. And we can see the nodal solution. And as you can see, the maximum displacement is happening where we are applying the force. So we can see the displacement in that way. And at the same time, we can print the nodal structure displacement with this line of code, PRN SOL, and then we can say U COMP. So you see now we have all results printed here, and we can see basically the displacement in the coordinate system. As expected, we don't have any displacement in Z direction, or what for any of these. For let's say node 1, UX is 0, UY is 0, UZ is 0, and then for 2, 3, 4, 5, we have the displacement as you can see in here. At the same time, we can find the maximum absolute values for node 3, 2, as you can see the value is, for example, 0.25 e to the power of -3. So that is how we can basically print the nodal solution for a specific node. So now we have the displacement. The question is how we can look at the forces and other parameters of the elements. So in order to do that, what I'm going to do is going to general post-processing, first clicking on result viewer. Then once we are done with that, I will write here PRESOL Okay, that is going to give us the force on every elements that we have in here, and then hit OK. So here we can see the forces on every elements and in X, Y, and Z direction. As you can see, for element 1, we have the forces as expected. For element 2, and then the other elements as well, right? So for element 1, 2, you see like we have 1 and 2, right? So 1 is the node 1 and 2 is node 2, and it is representing the force between these two elements, right? We have 2, 3, 1, 4, 4, 2, 2, 5, 5, 3, and 4, 5. Basically, we have 5 elements, and for each of them, we have obtained the force as expected in here, right? So we can see the value of forces from 1 to 2 and also from 2 to 1 in the form of reaction forces. So that is how we can print the forces, and that is how we can find the value of forces. So we can also look at other parameters like strain, right? So if I write here PRESOL ELEN and then hit OK, we can see the other parameters related to each nodes. like in here we can see the elastic string, right? So generally for basically solution and post-processing, we can write a single code on the command prompt and we can look at different parameters depending on what we expect and what we want for that specific example.